Somaiah, working as assistant professor in the Department of Mechanical Engineering. Welcome back to the course of Fluid Mechanics and Hydraulic Missions. So, today we are going to discuss the introduction regarding fluid missions, turbo machinery. In this fluid missions, we have different types of turbines. So, the turbines, what are the working proportions, working principles of turbine, and the velocity triangles of various hydraulic turbines, and what is the work done, otherwise power developed by the turbine, then governing of turbines, then characteristics of a turbine, various parameters we'll see in this fluid missions. So this comes under module 5. The hydraulic turbines are machines which use the energy of water and convert into mechanical energy. The turbine is basically which converts the hydraulic energy into mechanical energy. Again, that mechanical energy can be converted into electrical energy and so on. Basically, it uses the energy possessed by the water as an input, and it will be converted into mechanical energy. So the mechanical energy is nothing but which is going to be rotate the turbine shaft and thereby rotor, so that while it is connected to a generator, which is generating a power. So from this mechanical energy, these may be considered as a prime movers. The mechanical energy developed by a turbine is used in running an electric generator, which is directly coupled to shaft of the turbine to generate electric power. The electric generator thus develops electric power, which is known as hydroelectric power. So as there are different types of the turbines are there, gas turbines are there, and tidal power is also there. The geothermal power is also there. Steam turbines are there to generate steam power, etc. But whenever the hydraulic energy, the energy possessed by the water, is utilized for the development of a power, in such case, we have to call the particular power is known as hydroelectric power. So, since the generation of hydroelectric power is relatively cheaper than the power generated by other sources, so that's why majority of hydroelectric power stations are installed. If you compare with other steam energy or geothermal, etc., the majority of power is produced by hydroelectric power stations only in India. So about 70% of the power requirement is fulfilled with the hydroelectric power stations. Nowadays, a number of hydroelectric and multipurpose projects have been undertaken in our country in order to harness more and more power from the available water potential. The idea of utilizing hydraulic energy to develop mechanical energy has been in existence more than 2000 years. In the earlier days of water power development, water wheels made of wood were widely applied, so which used either in the energy of falling water or the kinetic energy of the flowing stream of water. Here we can see a overshot wheel. So here there is a wooden wheel with different curved blades. So we can see here whenever, so it is kept on one shaft, so over which the water is allowed to fall onto this wooden wheel. So due to that, the water force, the wooden wheel is he will be trying to rotate. While rotating, it rotates shaft also. So the shaft is connected to a generator which will be developing the power. In earlier days, they were using the wooden wheel. So later on, it is converted into the wheels made by alloys and metals, etc. But so in the overshot wheel, over the wooden wheel, the water will be from overhead. The water will be allowed to fall onto the wooden wheel. Due to that force, it will be rotating. So that is the idea. So gradually, it was turned into the turbines which we are using today. Undershot wheel. In undershot wheel, while the water flowing forcibly like this, so at some point, so in such a way that water has to hit this veins and below of this wheel, the whenever the water is applied, so below of this wheel, due to that force, the actually the buckets, the curved buckets will be impacted with this water force. Due to the force, so the runner tries to rotate. Whenever the water this is rotating, as it is coupled to a shock, so that is also rotating. So therefore, when a water is allowed from the bottom portion, whenever it is hitting on the buckets which are below. Now, if it is allowed, water is allowed to fall over the wheel, so then it is known as overshot wheel. And if it is allowed the water to hit the buckets of a wheel, so under, so then we can call it as a undershot. So water is flowing, but we are keeping under this water. The wheel is kept under the flowing fluid. So due to that force, it will be rotating. So this is the earlier days. These type of wheels and they were using. So wooden wheels. These are not much economical, not much power generating devices because so it will not it will not be because it won't accept too much. If the force heavy water impact is there, then it will be broken. As it is made up of wooden, it can't sustain such type of heavy hydraulic forces. So that's why, so gradually it was changed. So the turbines are basically the broader classification is there are two cases. One is impulse turbine, another one is reaction turbine. There are two types of turbine. One is impulse turbine, another one is reaction turbine. In the reaction turbine, again it will be classified into Francis turbine, propeller turbine, tubular, bulb, rim type, etc. So we'll see the definition of reaction turbine and impulse turbine and various examples of reaction and impulse turbine, why it is reaction, etc. So we will see while we are proceeding. So the impulse turbine example is a Pelton wheel turbine, Bunky cross flow turbine, etc. So in Pelton wheel turbine, so there will be these impulse and reaction turbines are differentiated with their working principles actually. So yeah, in the case of reaction turbine, this will be rotating, otherwise this will be working due to the difference of pressure. So the turbine will be rotated due to the pressure difference. So in previous cases, what is happening due to this water for pressure only? So the bucket is going to be impacted by this water force. Due to that, it is rotating. So, but here there is no particular principle is applied. There is no pressure difference, etc. So just we are controlling with the help of this gauge. The amount of the pressure and velocity will be varied, and it will be hitting underneath of the turbine. So therefore, later on, they using particular principle, they were rotating, they were running. So here, in case of impulse turbine, only to the our total available energy of a water will be converted into only kinetic energy. But in case of reaction turbine, there will be kinetic energy and pressure energy. Both kinds of energies are available. So that is a different another difference between impulse and reaction turbine. So here only the pressure difference, due to the pressure difference, the reaction will be taking place. Due to the pressure difference, the turbine will be rotating. But here only due to the kinetic energy, whenever here the water is hitting with the heavy kinetic energy on a wheel, due to that the runner will rotate. But in case of reaction turbine, not due to the only kinetic energy. Also there is a pressure energy. And the hydraulic turbines, Furtherly, they can be classified like this according to the type of energy at the inlet of a turbine. So, for any turbine, it can be said whether it is impulse or reaction turbine based on the available energy at the inlet. If the available energy at the inlet is only kinetic energy, then so that is a impulse turbine. Otherwise, the example is Pelton wheel turbine. So it uses only kinetic energy by converting remaining energies into the kinetic energy only. But if the inlet energy is comprising both kinetic energy as well as pressure energy, then that is known as reaction turbine. Based on our available energy, we can say available energy at the inlet to the turbine. We can classify. We can say whether it is impulse or reaction. So another one is according to the flow through a runner. So there are different types of flows where if you observe different in real turbines. So there will be a tangential flow, another one is axial flow, radial flow, mixed flow, etc. Based on the direction of flow, we can say which type of turbine also we can say whether it is axial flow or mixed flow, it is tangential flow, and what are the examples for that. We can say based on the direction of flow through runner through the runner. So according to the available head at inlet, so head at inlet means from the reservoir level to the turbine center. So before hitting, so while the water is taken from the reservoir through the penstock pipe, so here the reservoir will be somewhere here, but a turbine is installed at this place. So then the head indicates the difference between reservoir level to the turbine center. If it is 1800 greater than to 1800 meters, so we can say so the type of turbine is a impulse turbine. Example is Pelton wheel turbine again. So, but if this difference from the reservoir is less than 2, otherwise 250 to 60 meters, in between 250 to 60 meters, that is the medium flow turbine, medium head turbine, that is medium head turbine, not medium flow turbine. And less than to 60 meters is nothing but, so less than to 60 meters is the Kaplan turbine, the axial flow turbine. So, and this is a Francis turbine, otherwise mixed flow turbine. So, this is a tangential flow turbine, and Pelton wheel is the example. So, based on the available head to the inlet of a turbine. So, according to the specific speed of a turbine, the specific speed, we have to derive the specific speed. So, n root p by h power 5 by 4. Based on that, we can say high specific speed, medium, and low specific speed. Next, the position of a shaft. The shaft of a turbine can be positioned horizontally. Then you can rotate perpendicularly. Also, you can keep like this. Also, if it is like this, the rotor will be like this. Then water will be applied in this direction. Based on the type of turbine, it can be applied. There are two dispositions of a shaft. Here, so we'll see according to the type of energy available at the inlet of a turbine. So for which the example is the Pelton wheel turbine. So the this is a penstock. So if the reservoir is here, from the penstock the water will be taken, and it is going to be supplied to the turbine inlet. So, but at the inlet, I'm going to insert a converging nozzle like this. So area, so yeah, this diameter is constant throughout. But at the exit before hitting the turbine, I am keeping one converging nozzle. So due to this converging nozzle, the available energy of water, the pressure energy and kinetic energy, also potential energy, all these energies will be converted into only kinetic energy by converting like this. Here, the velocity will be increased. The pressure energy also will be converted into the kinetic energy only. So, with the kinetic energy of mv square, it is going to hit the turbine runner. The turbine runner is consisting of buckets. Water will be impacting on the bucket. So the jet is going to be impacting on a bucket. So while it is converting into kinetic energy, into one, while all the energy is converting into only kinetic energy. Such type of turbine is known as impulse turbine. Impulse turbine. And examples are turbo impulse and Pelton-wheel turbine, Girard turbine, Bank turbine, Joule turbine, etc. Similarly, yeah, in case of reaction turbine, there will be two kinds of energies will be there. See, only part of the available energy of water is converted into kinetic energy, but the substantial energy will be remained in the pressure energy. So, therefore, the reaction turbine is a combination of these two, pressure energy and kinetic energy. Both will be there. So, by using a scroll casing or spiral casing, if the diameter of scroll casing is gradually decreasing, so then there will be partial energy will be converting into kinetic energy, and the substantial amount of energy will be remained as pressure energy. These two energies there, with these two energies, it will hit the runner. As the water flow through turbine pressure, pressure energy converts into kinetic energy gradually. So it has to utilize the scroll casing, gradually decreasing diameter scroll casing, so that both the energies can be available before hitting the turbine. So, reaction turbine, at the entrance of runner, only part of the available energy will be converted into kinetic energy. The remaining, so that we have seen previously. And for this gradual change of pressure to possible, a runner must be completely enclosed in airtight casing. The completely enclosed airtight casing, that is the scroll casing. We have to utilize, we have to use the around the runner of a turbine. If you use a scroll casing with a gradually decreasing cross sectional area, then the both kinds of energies we can have. So the differences of pressure between inlet and outlet of runner is called reaction. So, but before coming into the turbine, so there will be different pressure where the inlet the pressure will be high. So after hitting the turbine vanes, and it causes the rotation of a runner, and after that it leaves from the exit, and there will be a draft tube to convert the low pressure into again high pressure in order to we convey the water from the exit of a turbine into the tail race. So the difference between exit of a turbine and inlet to the turbine, the difference between these two pressures is known as a reaction. Is called a reaction pressure, and the turbine which utilizes this principle and which is working means we can call it as reaction turbine. The difference of pressure between the inlet to the turbine and from the outlet of the turbine. The examples are Francis, Kaplan, Thomson, Fornieron, propeller turbine, and so on. According to the direction, there will be a tangential flow. Here we can see the what is tangential flow. So in detail, while we are discussing about the Pelton-wheel turbine, the radial flow, axial flow, and mixed flow. The mixed flow is a combination of radial and axial, and axial flow turbine, while the water, the liquid is flowing axial to the runner, but not it need not to coincide with the center of the turbine, but the direction of flow is axial. Radial means it may come axially and leave radially, so it go radially upward and radially downward. So this is axial flow. And mixed flow uses comes axially and leaves radially. So otherwise it comes axial and leaves downward. So the mixed flow turbine, the tangential flow turbine, where if the turbine is like this, the buckets are like this, backward curved vanes. Then if you draw a center line from all the centers of buckets. So then that the circle is known as a pitch circle. For that pitch circle, the water which is coming out of a jet, the center of a jet is tangential to the center of the center circle, the pitch circle, which is drawn from the centers of all the blades. So that the type of flow is known as a tangential flow, because the center of the jet is tangent to the pitch circle. So therefore, such type of flow is known as tangential flow. This is example of tangential flow. Next, so we can see the tangential flow. Here, the jet center line is this, and the line, this is a circle or pitch circle are drawn from the centers of all the buckets. So this center line of a jet is, which is coinciding with a pitch circle, they are not coinciding, passing tangentially. So therefore, this type of condition is known as a tangential flow turbine. In the radial flow, the water flows in the radial direction through the runner. So inward radial flow will be there. The water enters the outer circumference, so like this, and leaves radially in inward and or outward. The old Francis turbine is the example. The outward radial flow, the water enters at the center and flows radially outwards. So the outer periphery of the runner. The axial flow turbine. The water flows through the runner only and mainly along the direction parallel to the axis of the rotation, parallel to the axis of the rotation. So not tangential. So not radial, not tangential. The mixed flow turbine means which uses the axial flow and radial flow. So comes axially and leaves radially. Water enters at the runner periphery in the radial direction and leaves it at the center of the axial direction. So parallel to the rotation of the runner. So the example is the modern Francis turbine. So outer periphery is radial and leaves at the center axially. So therefore this is which employs both the radial and axial directions. According to the head available at inlet, high-head turbines, these are above 250, above 1800. So 255 meters to 1770 meters. So that type of turbine is pattern wheel turbine. The head, the reservoir level to the turbine center. So medium head turbine. These turbines are capable of working under the medium. It's ranging from 60 to 250 meter. So above 250 meter and 60 to 250 meter is medium, and below 60 meters is low head, and medium head turbine is Francis turbine, and also mixed flow turbine. This is mixed flow turbine. The Pelton wheel turbine is a high head turbine, but it is a tangential flow turbine, tangential, not axial. It should not be called as axial turbine. Low head turbine is less than 260 meters. So example is Kaplan turbine and propeller turbine. So these are axial flow turbines. These are axial flow turbine. Therefore, Kaplan turbine is a low head plus axial flow reaction turbine. According to the specific speed, so there are three kinds of turbines. The actual specific speed is the speed of geometrically similar turbine that would develop 1 kilowatt power when working under unit head, working under a head of 1 meter. So such type of speed for a geometrical similar turbine is specific speed. Low specific speed is Pelton wheel, but this is high head. This is a high head turbine. So its specific speed is 8.5 to 30. So medium specific speed is 50 to 340. The example is Francis turbine, medium. So low head turbine, Kaplan turbine, which will be giving high specific speed. Okay, according to the position of a shaft. This is a vertical disposition of a shaft. So there will be horizontal disposition and vertical disposition. Horizontal, vertical. There are two kinds of positioning of a shaft. So in general, the general layout of a hydroelectric power station is, so there will be a reservoir against which the dam will be constructed like this. This is known as head race, and the H1 gives the gross head. This is the total head, but this line indicates the losses. So the loss of head due to friction, inlet loss, the loss due to the change in direction of a fluid, and due to the pipe fitting coefficients, and different losses will be there. Therefore, the energy will be water energy before hitting the turbine is varying like this. Now, this is a penstock, which is a device, the way a pipe which is conveying the water from reservoir to the turbine inlet. So, at the exit of your turbine, here we are using one converging nozzle. So, in case of a Pelton wheel turbine, if you use converging nozzle, converting the all available energy of water into only kinetic energy, we can call it as impulse turbine. Then it is hitting the runner blades, so that it is generating a power. So after hitting, the water will be falling into the tail race in this tank. Say the top surface of this is known as a tail race, and the top surface of a reservoir liquid level is head race. You see the head race and tail, the difference between these two levels is known as gross head. And say if it is a datum line, so there you can take a Z1, Z2, etc. in order to draw hydraulic gradient line and total energy line. Hydraulic gradient line is a summation of potential energy or potential head and pressure energy P by rho g. So similar total energy is summation of P by rho g plus V1 square by 2g plus Z. So in order to calculate all this, and to construct a total energy and hydraulic gradient line at various points, we have to install the piezometers. Then we can calculate and we can construct the total energy line and hydraulic gradient line. The head and efficiency of hydraulic turbines. We use the gross head. The gross head is defined as the difference between the head raise level and tail raise level, as we have seen in this picture. The difference between the head raise and tail raise. This is the water level in a tail raise. This is the water level in the reservoir. So the difference between these two is gross head. The net head or effective head is the head available at the entrance to the turbine. Before hitting the turbine, the available head is known as net head, with which it is the effective head with which it is hitting the turbine. So this is the available head after removing the losses. So therefore, the net head is defined from tail race to the total energy line, the gap between, because this gap indicates losses. Net head is H1 minus HF. So H1 is gross head. If you subtract losses from that, then you will get the net head. The hydraulic efficiency of a turbine. So that is the ratio of the power developed by the runner and the power given to the power. The ratio of the power developed by the runner to the net power supplied to the water, supplied by the water. So the power developed by the runner is, so we have to estimate the what is we can find out the work done or developed by the work done given by the turbine. So there are equations, but the water given by the jet. So net power supplied by the water is rho g QH. This is a specific weight into a discharge into head. So the specific weight is rho g. QH is the water energy. So water, this is the inlet energy given by the water to the runner, so that by utilizing this energy, the runner starts rotating. So then how much of power developed by the runner? So that we will calculate. The power developed by the runner to the inlet power. Inlet power is water and water only. Therefore, hydraulic efficiency means, so what is the hydraulic energy given by the water to the runner to rotate? So we can find out this one by calculating based on different turbine. With different turbines, we have to find out the work done developed by the turbine. So that is vary from turbine to turbine. But inlet power is rho g QH, the power given by the turbine. Therefore, this is hydraulic efficiency. Next one, mechanical efficiency. The power available at the turbine shaft to the power developed by the runner. So the power developed by the runner, this is due to the water. It utilizes the water energy It utilizes the water energy, and it develops the power. So by utilizing the water energy only, the turbine rotor starts rotating. Well, the turbine rotor starts rotating, so it rotates the shaft also. Then at the exit of a shaft, at the turbine shaft, available power due to the power developed by the runner is mechanical efficiency. But here we should not utilize the power developed due to the water. So if you consider power developed by consuming the water energy, how much of the power developed by the runner is hydraulic efficiency if you use the water energy. So, but if you use after consuming the water energy, the turbine rotor is rotating, but it is rotating shaft also. So, the power available at the shaft is divided by the power developed by the runner. So, therefore, it is mechanical efficiency. The volumetric efficiency. The volumetric efficiency is the ratio of quantity of water actually striking the runner and the quantity of water supplied to the turbine. So how much of water is actually supplied to the turbine, Q plus delta Q. So there are some losses. So the what is the striking water and how much of water is supplied to the turbine. The ratio of these two is volumetric efficiency. The overall efficiency is a product of hydraulic efficiency, volumetric efficiency, and mechanical efficiency. Otherwise, mechanical efficiency into hydraulic efficiency. But the overall efficiency means at the exit of a turbine shaft, what is the power available, and but the net energy given to the turbine entrance. At the turbine entrance, what is the available energy? Before hitting the turbine, what is the available energy? After hitting, the turbine starts rotating. After rotating, it rotates the shaft coupled to a runner. So the power available at the exit of a shaft, what is the available power by at the inlet, total outlet. This is our total outlet, and this is inlet. So the ratio of these two is known as overall efficiency. Otherwise, the product of hydraulic efficiency and mechanical also. Otherwise, product of these three efficiencies. These are the references. Thank you.
Like, share, and subscribe. Hit the bell icon for more updates.